Imagine ordering a cup of coffee, but instead of getting a full cup, half of it is just foam. You're paying for a full cup, but you're not getting the real thing. That's exactly what happens in electrical systems when the power factor is low. The more foam, or wasted reactive power, in your system, the more energy is wasted, leading to higher electricity bills. But what is power factor exactly? Why does it matter? And how can we correct it to avoid unnecessary costs? In this video, we'll break it all down in a clear and practical way so you can understand power factor and improve it in your electrical system. Think of a low power factor like ordering a sports car, but only getting a lawnmower engine under the hood. You're not getting the performance you paid for. Let's get started. What is power factor? Power factor, or PF, is the ratio between real power, measured in kilowatts, and apparent power, measured in kilovolt amperes, in alternating current electrical circuits. It is calculated using the formula power factor equals real power divided by apparent power. If the power factor is close to 1, most of the power is being used efficiently. A low power factor means that a significant portion of the power is wasted as reactive power, which increases electricity costs. For residential users, homes, and small businesses, typically electricity bills are based only on real power, measured in kilowatts, and total energy consumption, measured in kilowatt hours. Reactive power, measured in kilovolt amperes reactive, is not separately charged. This means power factor is not a major concern for small consumers. For industrial and large commercial users, these consumers are billed based on either apparent power, measured in kilovolt amperes, or real power, measured in kilowatts. If the billing is based on apparent power, a low power factor increases electricity costs because the system draws more current than necessary. A low power factor increases the load on the electrical grid, leading to higher energy losses and the need for larger transformers and thicker cables to handle the extra current. This reduces overall efficiency and increases infrastructure costs. Just real-life application. Imagine a factory running a water pump. The pump requires 50 kilowatts of real power to operate, but the factory is billed based on apparent power, which is 70 kilovolt amperes. Let's calculate the power factor. Power factor equals real power divided by apparent power. Power factor equals 50 kilowatts divided by 70 kilovolt amperes. Factor equals 0.71. Since this power factor is low, well below 0.9, the utility company may charge penalty fees for excessive reactive power consumption. That extra energy is wasted, yet the business still has to pay for it. It's like renting a car that burns more fuel than necessary, wasting money for no reason. Understanding power factor. Using the power triangle. The power triangle is a fundamental concept in electrical engineering that visually represents the relationship between the three key electrical quantities in alternating current power systems. Power factor can be understood using this triangle, which consists of 1. Real power measured in kilowatts. This is the useful power that performs actual work, such as running a motor or lighting a bulb. 2. Reactive power measured in kilovolt amperes reactive. This is the non-working power required to create magnetic fields in inductive loads like transformers and electric motors. 3. Apparent power measured in kilovolt amperes. This is the total power drawn from the electrical supply, combining both real power and reactive power. The power factor represents how efficiently electrical power is being used. A higher power factor means more real power is utilized effectively, reducing losses and improving system performance. Imagine you're riding a bicycle. If you pedal straight forward, all your energy moves you ahead efficiently. This is like having a perfect power factor of 1, but if you lean sideways while pedaling, some of your effort is wasted in maintaining balance instead of moving forward. This is similar to a low power factor, where part of the energy is lost as reactive power. It's the same as trying to row a boat with just one oar. You'll waste energy going in circles instead of moving efficiently. The power triangle in AC systems. The power triangle is a mathematical representation of the relationship between three types of power in an alternating current system. Real power, P, measured in kilowatts, which performs actual useful work. Reactive power, Q, measured in kilovolt amperes reactive, which does not perform work but is necessary for inductive loads. Apparent power, S, measured in kilovolt amperes, which is the total power drawn from the source. The power triangle is based on basic trigonometry, forming a right triangle where real power is the adjacent side, reactive power is the opposite side, apparent power is the hypotenuse. Instead of memorizing complicated equations, just visualize the power triangle. It makes understanding power factor much easier. Why does power factor drop, and what hidden cost does it bring? Many factories with large electric motors receive expensive penalties on their electricity bills due to poor power factor. Have you ever wondered why power factor is low? Here are some common reasons. Inductive loads. Devices like electric motors, transformers, and solenoids require reactive power to create magnetic fields, leading to a lagging power factor. Capacitive loads. Some LED lighting and power supplies can cause a leading power factor, which can also be problematic. Unbalanced load distribution. Running different types of electrical equipment simultaneously may cause fluctuations in power factor. Lighthearted note. If power factor were a person, it might be that friend who always shows up late because they got distracted on the way, causing delays and extra energy expenditure. Practical example, power factor correction calculation. Let's consider a factory with the following power details. Real power consumption, 50 kilowatts, current power factor, 0.78, target power factor, 0.96. Calculation steps. Step 1, calculate apparent power before correction. Apparent power is determined using the formula, apparent power equals real power divided by power factor. Apparent power equals 50 divided by 0.78, approximately 64.1 kilovolt amperes. Step 2, calculate reactive power before correction. Reactive power is calculated using the power triangle formula. Reactive power, old, equals the square root of apparent power squared minus real power squared. Reactive power, old, equals the square root of 64.1 squared minus 50 squared, approximately 40.1 kilovolt amperes reactive. Step 3. Calculate required reactive power. After correction, first determine the new apparent power at the target power factor. New apparent power equals real power divided by target power factor. New apparent power equals 50 divided by 0.96, approximately equals 52.1 kilovolt amperes. Now calculate the new reactive power. Reactive power, new, equals the square root of new apparent power squared minus real power squared. Reactive power, new, equals the square root of 52.1 squared minus 50 squared, approximately equals 14.6 kilovolt amperes reactive. Step 4. Determine the capacitor rating needed. The required capacitor rating is the difference between the old and new reactive power. Capacitor rating equals reactive power, old, minus reactive power, new. Capacitor rating equals 40.1 minus 14.6, approximately 25.5 kilovolt amperes reactive. Result, to improve the power factor from 0.78 to 0.96, we need to install a capacitor bank rated at 25.5 kilovolt amperes reactive. This will reduce energy losses, lower electricity costs, and improve system efficiency. How to improve power factor. Boosting power factor helps cut energy costs. Here's how. 1. Install capacitors. They offset reactive power from inductive loads, improving efficiency like tiny energy-saving heroes. 2. Use inductive reactors. In rare cases of excessive power factor, reactors help balance it, like brakes on a speeding car. Apply automatic power factor controllers, APFCs. These smart systems adjust capacitors in real time, ensuring optimal power use. Reduce unnecessary loads. Running only essential equipment minimizes waste, like decluttering for better efficiency. Power factor is a critical concept in electrical systems. Improving it leads to energy savings, lower electricity bills, and better equipment efficiency. If you found this video helpful, don't forget to like, subscribe, and share it with others. Also, check out our Udemy playlist on electrical power management for more in-depth tutorials. I'm Abdul, thanks for watching, and I'll see you in the next video.